Every second, the universe reveals mysteries that defy our understanding of existence. From dazzling galaxies twinkling with countless stars to mysterious phenomena that baffle even the brightest minds, space is a treasure trove of enigmas waiting to be explored. Join us today as we explore the greatest mysteries in the universe. The universe is a vast and mysterious place, filled with celestial objects that baffle our understanding of space. One of the most unusual types of objects discovered is a neutron star. This incredibly dense remnant of supernova explosions contains two stellar masses similar to the Sun, but is only 20 kilometers across. A teaspoon of neutron star material would weigh as much as an elephant here. These stars rotate at incredible speeds, sometimes completing a revolution in a matter of milliseconds, and they often emit beams of radiation across space like beacons, creating what we know as pulses. Another interesting celestial body is the ugly planet. Unlike typical planets orbiting stars, asteroids travel through space without a solar system. Hypothetically, there could be billions of these lonely wanderers in our galaxy. Some scientists speculate that they formed around stars before being ejected by gravity. The existence of these planets complicates our understanding of planetary formation and dynamics, and shows how complex and unpredictable cosmic processes are. Black holes are probably the most interesting things in the universe. In these regions of space, the gravitational pull is so strong that nothing, not even light, can escape. Although we cannot see black holes directly, we can infer their presence by observing the behavior of nearby stars and gas clouds. A remarkable discovery is that supermassive black holes are at the centers of many galaxies, including our own Milky Way. These giants contain millions or even billions of solar masses and can influence the formation and evolution of their galaxies. Finally, we have a look at dark matter. Although not a celestial entity, its presence is felt throughout the universe. Making up about 27% of the universe, dark matter affects the motion of galaxies and galaxy clusters, but it does not emit, absorb, or reflect light, making it undetectable by traditional means. This mysterious substance has led scientists to unravel its mysteries, making it one of the most fascinating discoveries in modern astrophysics. Each of these unusual objects and phenomena provides a glimpse into the amazing fabric of the universe and sparks interest in what lies beyond our planet. Neutron stars and black holes are both remnants of massive stars, but they differ in their physical properties and their environments. When a massive star runs out of nuclear fuel, it leaves the core and undergoes a supernova explosion. If this core is about 1.4 to 3 times the mass of the Sun, it becomes a neutron star. Neutron stars are incredibly dense. So much sugar cube-sized neutron star material would be the same as an entire mountain. They consist primarily of neutron particles that are tightly packed together, resulting in strong gravitational and electromagnetic fields. Black holes form when the core of a star collapses under its own gravity and passes a critical mass threshold. This creates a gravitational force that nothing, not even light, can escape from. The boundary around a black hole is called the event horizon. Within this limit, the laws of physics begin to break down. We can observe the effects of black holes, such as the acceleration of nearby material and X-rays. Black holes themselves are not visible to direct observation. We often find pulsar activity around neutron stars. A pulsar is a type of neutron star that emits radiation from its magnetic poles. As these stars rotate, the rays travel through space, creating constant pulses similar to cosmic beacons. This phenomenon allows astronomers to detect pulsars with their periodic signals. Neutron stars can also form binary systems with their companion stars. creating dynamic interactions that can lead to the emission of powerful jets and X-rays. Conversely, black holes can create incredibly energetic jets, especially around supermassive black holes found at the centers of galaxies. The nearby material forms an accretion disk, an elongated region of gas and dust, heated to extreme temperatures and emitting bright emissions in the electromagnetic spectrum. This cosmic dance of matter and energy reveals the fascinating and extreme conditions around neutron stars and black holes, revealing their role as some of the most fascinating objects in the universe. Quasars, or quasi-stellar objects, are incredibly bright celestial objects found in the far reaches of the universe. They were first discovered in the 1960s and were initially thought to be stars because of their brightness, but further research has revealed that they are among the most energetic objects in the universe. This light comes from supermassive black holes at the center of distant galaxies, surrounded by disks of gas and dust that are intruding into the black hole. As the inner material spirals, it accelerates and forms an accretion disk, producing massive amounts of energy that often outshine entire galaxies. One of the reasons quasars are considered such powerful energy sources is the process by which gravitational energy is converted into light. As gas and dust fall toward the black hole, the massive gravitational pull creates high temperatures, causing the material to glow brightly in the electromagnetic spectrum. This includes visible light, ultraviolet light, and radio waves. In fact, some quasars emit more energy than all the stars in their galaxies, which span billions of light years. Quasars also serve as important tools for understanding the universe. They act as cosmic beacons, helping astronomers measure the expansion of the universe and the distribution of matter in the vast voids between galaxies. By studying the light from quasars, scientists have been able to learn about the composition and behavior of intergalactic matter, as well as the conditions that existed in the early universe. Finally, quasars remind us of the dynamic and changing nature of space. They are not static phenomena. Some show large changes in brightness over short periods of time, suggesting the chaotic and dramatic environment around supermassive black holes. Each quasar is a testament to the amazing forces at work in our universe, revealing the fascinating interplay between gravity, light, and cosmic evolution. Exoplanets, planets outside our solar system, are of increasing interest to scientists and space enthusiasts, especially those living in their star's habitable zone. This zone, known as the Goldilocks zone, is the region around a star where liquid water should be present on the planet's surface. Having liquid water is essential because it is a fundamental component of life as we know it. These exoplanets may have different characteristics, but they share some common traits. They orbit the stars at the right distances so that water can remain in liquid form. In addition, many of these planets have atmospheres that protect the surface environment from harmful radiation and can regulate temperature. Some may even have Earth-like geological features, such as mountains, valleys, and potential signs of past or present water flows. It is worth noting that the search for exoplanets in the habitable zone is a key part of our study of life beyond Earth. Finding a planet within this zone increases its chances of sustaining life. Astronomers often focus on stars similar to our Sun because they will host planets in conditions comparable to ours. The discovery of planets like Proxima Centauri b, located just 4 light-years away, has sparked interest in space exploration and the potential for future missions to uncover signs of extraterrestrial life. The study of exoplanets in the habitable zone not only increases our understanding of the universe, but also provides insights into the origins of life on Earth. By probing these distant worlds, we can gather information about atmospheric composition, surface conditions, and even the potential for life. As technology advances, the search for these intriguing planets continues, fueling dreams and hopes that we may one day find interstellar neighbors. Gas giants such as Jupiter and Saturn offer unique features that distinguish them from terrestrial planets such as Earth and Mars. First of all, their size is amazing. Both of these gas giants are huge, with Jupiter being the largest planet in our solar system, taller than Earth and 11 times larger in diameter. Saturn, although a little smaller, has a huge presence with its iconic rings, which are awe-inspiring to observe. Their large scale not only sets them apart, but also affects their unique atmospheric conditions. Another compelling characteristic of gas giants is their composition. Unlike the terrestrial planets, which were originally made of rock and metal, Jupiter and Saturn are composed mostly of hydrogen and helium. In fact, they have a thick atmosphere that extends deep into the interior. As they descend into their clouds, the temperature and pressure increase dramatically, causing interesting phenomena such as metallic hydrogen on Jupiter and violent storms that last for hundreds of years. The most famous of these storms is the Great Red Spot, a storm larger than Earth itself. The presence of rings is another interesting feature that distinguishes Saturn from the terrestrial planets. Although Jupiter, Uranus, and Neptune all have ring systems, Saturn's rings are the widest and brightest and are made up of ice and rock particles. These rings vary in composition and density, creating a stunning display. Observing them reveals a complex dance between celestial bodies, revealing a dynamic environment with bumps and tides caused by the gravitational influence of Saturn's moons. Finally, the large number of moons orbiting these gas giants adds to their intrigue. Jupiter alone has more than 60 confirmed moons, including the largest moon in the solar system, Ganymede, which even surpasses the planet Mercury. Saturn boasts an impressive set of moons, with Titan standing out because of its thick atmosphere and surface lakes of liquid methane. These moons offer a variety of environments and conditions, offering scientists many opportunities to study early Earth-like processes and even hold the potential for extraterrestrial life. By studying these features, we not only learn more about the nature of the solar system, but also enhance our understanding of planet formation and evolution through space. Comets are objects in the sky often called dirty snowflakes. They are made primarily of ice, dust, and various organic compounds. This unique composition plays an important role in determining how the comet behaves as it approaches the Sun. As a comet travels inward from dark, cold space, heat from the Sun causes the ice within it to sublimate, turning directly into a solid gas. This process ejects gas and dust particles, forming a glowing cloud around the nucleus called a coma. A comet's tail is one of its most interesting features, and its composition directly affects it. As a comet approaches the Sun, sunlight and the solar wind, a stream of charged particles emitted by the Sun, push away gas and dust particles. Depending on the composition of the comet, different gases can be emitted, which causes the tail to change in color and characteristics. The tail is usually made up of two parts: a dust tail that follows the comet's orbital path, and a gas tail directly from the Sun, creating a spectacular visual display. Not all comets behave the same. Their activity and tail formation may vary depending on the material. For example, comets rich in volatile compounds may exhibit more vibrant tails and higher activity levels. On the other hand, those with a large amount of rock and little ice can produce weak tails. This option supports the different appearances of comets, making each encounter unique and interesting. As comets move closer to the Sun, their behavior is often more chaotic and unpredictable. Depending on their structural integrity and the intensity of the Sun's heat, they may break into smaller pieces or even disintegrate completely. Each provides a glimpse into the basic material that forms our solar system, allowing scientists to better understand the conditions of our cosmic neighborhood while awe-inspiring with their spectacular views. The discovery of exoplanets is an exciting development in our understanding of the universe. These worlds, drifting through space untethered to a single star, defy long-held assumptions about planet formation and stability. Historically, we thought that planets formed only in the gravitational embrace of their host stars, where they could collect material and share systems with other celestial bodies. The existence of rogue planets suggests that the universe is much more dynamic and diverse than we thought. One of the most exciting aspects of malefic planets is their number. Scientists estimate that there may be billions of these lonely wanderers in our galaxy, even more than there are stars. This raises interesting questions about how many other planets might be hidden in the fabric of space that we cannot see. These planets could have formed around stars through processes other than gravity, such as gravitational encounters with larger bodies. Their presence represents a wild past for many star systems, as planets that once belonged to families can become lone adventurers. The presence of exoplanets not only expands the conceptual framework of planetary systems, but also opens up new avenues of exploration and interest. Scientists are investigating whether these planets, even without stars, could support life. It appears that exoplanets may retain heat from radioactive decay or have subsurface oceans, which could provide inhospitable conditions for microbial life. Such possibilities encourage us to rethink the conditions under which life could develop outside the habitable zones around stars. Ultimately, the study of dwarf planets reminds us of the complexity of our universe and the many mysteries that still lie ahead. Each discovery, such as these wayward orbs, adds a layer to our cosmic story, inviting us to re-examine what we know and examine the consequences of planetary motion in space. The journey of these planets, roaming freely through the galaxy, makes us think about our place in the universe. Spiral galaxies are among the most prominent structures in the universe. They are characterized by distinctive spiral arms that radiate from the central galaxy. These arms are often made up of young stars, gas, and dust, giving them their bright and colorful appearance. The central bulge, home to massive stars, is typically yellow and may contain a supermassive black hole at its center. The overall structure creates a disk shape that is bound by gravity and becomes quite flat. In contrast, elliptical galaxies lack this spiral structure and often show a rounded, three-dimensional appearance. They can range in shape from spherical to nearly oblong and consist primarily of older stars, which contributes to their overall red color. The gas and dust abundant in spiral galaxies are absent in ellipticals, resulting in star formation. This means that elliptical galaxies grow more slowly over time because they don't have enough raw material to form new stars. Another difference is in their star population. Spiral galaxies have a mixture of stars at different stages of life, from young blue stars in their arms to mature ones. Elliptical galaxies are mostly inhabited by massive stars, resulting in a uniform appearance. This difference reflects their separate histories. Spiral galaxies are often associated with star formation, while elliptical galaxies are typically depleted of star-forming material. Finally, the behavior and dynamics of these galaxies are also different. The rotation of spiral galaxies is evident because their arms create a circular motion. The motion of stars in elliptical galaxies is random. This randomness can lead to collisions and interactions that cannot occur in the orderly rotation of spiral galaxies. Understanding these characteristics helps astronomers piece together the evolution of galaxies, shedding light on the vast and complex history of our universe. The Milky Way, our galaxy, is an excellent example of the dynamic processes that shape galactic evolution. Its formation began 13 billion years ago, from a large cloud of gas and dust within the early universe. Under the influence of gravity, these materials began to clump together, forming the first stars. Over time, these stars formed clusters that merged and became the rich structure we know today, complete with stars, planets, and various celestial phenomena. As the Milky Way grew, it accumulated mass through a mechanism known as hierarchical accretion. Hence, it was gradually formed by the merger of smaller galaxies and dark matter halos. This process is thought to have helped form the galactic disk, where we find bright spiral arms filled with young stars. The center of the Milky Way likely hosts a supermassive black hole, a common feature for large galaxies that acts as both a giant anchor and a source of fascinating astronomical phenomena. In governing the universe, the Milky Way is not alone. It exists in a group of galaxies called the Local Group, which contains more than 50 galaxies. Among them, the Andromeda Galaxy is the largest and, like the Milky Way, is a spiral galaxy. The Local Group contains an interesting mix of galaxy types, from dwarf galaxies to giant spirals. The gravitational pull between these galaxies affects their shapes, motions, and interactions, creating a dynamic environment that reveals the complex nature of cosmic relationships. Interestingly, the future of the Milky Way is tied to Andromeda. In about 4 billion years, current models show these two galaxies colliding. This event will cause a dramatic reorganization as they merge to form a new galaxy, possibly changing the structure and stellar distribution of the two. The dance of the Milky Way and its neighbors reflects not only the past and present dynamics of our cosmic neighborhood, but also the incredible changes that will take place in the universe. Dark matter remains one of the most tantalizing mysteries of astrophysics. About 27% of the universe is invisible and interacts only with gravity. This material does not emit, absorb, or reflect light, making it undetectable with traditional telescopes. But its existence is derived from the gravitational influence that gives rise to visible matter, radiation, and the large-scale structure of the universe. One of the strongest lines of evidence for dark matter is in the way galaxies rotate. When astronomers observe spiral galaxies, they see something strange. According to Newtonian physics, the stars in the outer edges of these galaxies should be moving more slowly than in the center where most of the mass resides. However, measurements show that stars far from the galactic center are traveling at incredibly high speeds, suggesting that they must be influenced by an unseen mass. This discrepancy suggests that the abundance of dark matter around galaxies is far beyond what we can detect. Further intrigue arises when considering galaxy clusters. These massive structures contain hundreds or even thousands of galaxies gravitationally bound together. The motion of these galaxies within clusters is also indicative of dark matter. When calculating how much mass is needed to hold these clusters together based on visible components, the numbers always fall short. Observing mass through gravitational lensing, where light from distant objects bends around a larger object, provides a clearer picture, revealing that the largely invisible mass due to dark matter is needed to account for the gravitational pull in these systems. The influence of dark matter extends back to the formation of galaxies. Research shows that dark matter combines ordinary matter to form stars and galaxies. Interestingly, without dark matter, galaxies would not have formed at all because there would not have been enough gravity to hold the matter together. These interactions not only affect the structure and motion of galaxies, but shape our understanding of the evolution of the universe, making dark matter a key topic in our quest to unlock the mysteries of space. When galaxies collide, they create an incredibly chaotic yet fascinating environment. Imagine two massive stars, a collection of gas and dust, moving together under the force of gravity. As they begin to interact, their gravitational fields become intertwined, disrupting their shape and triggering a series of events that can spark the birth of new stars. During these collisions, regions of high density form between the compressed debris and the gas. These dense regions are important because they provide the right conditions for star formation. As gas clouds become more dense, they cool, and under the right conditions, they begin to collapse under their own gravity. When the temperature and pressure within these collapsing clouds reach a certain threshold, nuclear fusion burns out, resulting in the formation of new stars. The visual spectacle of the formation of a galaxy is breathtaking. Astronomers often take pictures of these colliding galaxies, revealing tales of stars and gas stretching across space. Bright bursts can often be found, indicating the formation of new stars as large clouds of gas ignite in a bright display. This process, known as interstellar activity, can produce hundreds, sometimes thousands of stars over a few million years. Interestingly, although this may seem catastrophic on a grand scale, the outcome of such cosmic collisions is constructive. Many new stars form from merging materials, enriching galaxies over time. This cycle of collision, formation, and evolution illustrates the dynamic nature of our universe, teaching that destruction can also give way to creation and new beginnings among the stars. Irregular galaxies are interesting celestial objects that differ from the familiar spiral and elliptical galaxies. They lack a distinctive shape, which is one of their defining characteristics. Instead, you can observe a chaotic arrangement of stars, gas, and dust, often with scattered young, bright stars. This lack of structure is usually the result of gravitational interactions with other galaxies, which can distort their shape over time. One of the most interesting features of irregular galaxies is their rich star formation activity. Many of these galaxies are home to young, hot stars that produce new stars more actively than their more orderly counterparts. This intense star production can provide astronomers with valuable information about the conditions and processes that lead to star formation in the universe, especially in regions less affected by the gravitational pull of neighboring galaxies. Irregular galaxies can also serve as a window into the early stages of galaxy development. Because they often lack the stable structures found in older galaxies, they are thought to represent an early stage of galactic evolution. Studying these galaxies helps scientists understand how galaxies form and evolve over billions of years. As this work in progress imagines, each disordered galaxy tells a story about the complex interplay of forces at play in space. In addition, these galaxies can provide information about the universal history of dark matter and cosmic structures. The dynamic and often unstable nature of disordered galaxies suggests that their environments are strongly influenced by experiences that affect their eventual evolution into structured forms. Thus, by studying irregular galaxies, we understand not only their unique properties, but also the larger story of cosmic history and galaxy formation. Satellite galaxies are smaller galaxies that orbit larger galaxies, called host galaxies. This dynamic relationship is a complex dance between the effects of gravity and dark matter diffusion. As these satellite galaxies move through the gravitational pull of their host, they can experience a variety of interactions that have profound effects on both galaxies. One of the most prominent effects of this interaction is the gravitational pull. It is formed when the gravitational pull of a satellite galaxy pulls in its stars, gas, and dark matter. Over time, this can cause the satellite galaxy to lose a significant portion of its mass, change its structure, and eventually collapse. 175,000 light-years away in the southern hemisphere's night sky in the constellation, Golden Fish is a truly massive object. NGC 2070 is an emission embolus, better known as tarantula. This tomb is gigantic and is believed to be the largest tomb known to date. This image shows one of the brightest space objects observed by Earth. To this day, there is no astronomer who has not heard of this cosmic miracle. The Tarantula Nebula is now the birthplace of stars. Earlier, behind the same powerful observational equipment, it was thought to be one of the brightest stars in the night sky, ahead of the constellation Goldfish. Nicolas Louis de l'Aquila was the first to recognize his true nature in 1751. Also, recent observations with modern telescopes have shown that this cosmic object is not a star at all, but rather a star in the sky. The size of this space object is huge. Imagine that this dome is about 1,000 light-years in diameter. If the closest object to us were replaced by the Orion Nebula, it would cover a third of the night sky. It would be 60 times larger than our familiar moon. He couldn't tear himself away from such a picture of the night sky. This dome overlooks the Milky Way's companion galaxy, the Large Magellanic Cloud. This emission is a large region of ionized hydrogen from which new stars form. Sources of ionizing photons are young, massive stars. Large dwarf stars are also powerful sources of radiation, producing large cosmic dusts of interstellar gas and dust. This is a very interesting phenomenon. These objects are formed by the gravitational influence of Tumbula's giant stars. Under this influence, gases explode, thus forming bulk-like shapes. Some stars explode in supernovae, most of which are illuminated by X-rays. That's why the Stellantis Nebula is so bright that we can observe it with the naked eye. Of course, for this you need to go to the southern hemisphere, and to see the exact outline of this space object as well as to see some of its great details, it is better to bring a good home or semi-professional telescope. But the VLT survey telescope at the European Southern Observatory in Chile was able to capture this dwarf and its rich stars in great detail. Here, for example, you can see the cosmic landscape of various star clusters, glowing gas clouds, and scattered debris from supernova explosions. Tarantula Nebula is named after its resemblance to the venomous spider tarantula. Its central part is similar to its body and contains large and bright stars. The spider's legs are clusters of gases, mostly hydrogen. The region itself is filled with this chemical element, but this giant spider is really kind. Tarantula's legs hug one of the largest cosmic objects known to us, the star cluster NGC 2070, an active star-forming region, and at its dense center, R136 contains one of the largest and brightest stars. With the Hubble Space Telescope's unique ability to capture ultraviolet light, researchers have been able to detect monster stars in the R136 star cluster that are 100 times more massive than the Sun. It automatically studies the largest collection of stars we know of. This cluster was first known to contain massive stars 50 times more massive than the Sun, and a new study found that R136 contains at least 9 stars with a mass 100 times that of the Sun. Notable among them is R136A1, the current record holder for a massive star, which is 250 times more massive than the Sun and is considered the heaviest star in the known universe. Not only are the stars very massive, they are also very bright, about 30 million times the luminosity of the Sun. Astronomers were also able to study the emission of matter from these animals in the ultraviolet range. Over the course of a month, they emitted a mass comparable to that of Earth, which is 1% of the speed of light. With such parameters, it is believed that the flow of matter leads to a very rapid mass loss. Astronomers are still trying to explain the origin of such giant stars. These giant stars are thought to have formed from the merger of less massive stars in smaller binary systems. This cluster contains another interesting star cluster called Hodge 301, where at least 40 stars have exploded as supernovae, spreading envelopes of gas across the region. One example of a supernova remnant is a star cluster known as SNRN 157b, which contains the scattered star cluster NGC 2060. The cluster was discovered by British astronomer John Herschel in 1836, using an 18-inch reflector telescope at the Cape of Good Hope in South Africa. Outside the Tarantula Nebula, The famous supernova SN 1987A can be seen in its lower right region. A supernova was the first star observed by modern telescopes since Kepler's observations in 1604. SN 1987A's light was so intense that within months of its discovery in 1987, it emitted 100 million solar powers. But if you look to the left of this image, you can see another diffuse star cluster called NGC 2100, which shows us a collection of blue stars surrounded by red stars. This group was discovered by Scottish astronomer James Dunlop in 1826 while working with a 23-centimeter reflector in Australia. The nebula also contains the star cluster and emission Embolus NGC 2074, another large star-forming region. If you look closely, you can see a dark, dusty structure in the shape of a seahorse. This feature is called the Seahorse in the Large Magellanic Cloud. It's actually a long columnar structure 20 light-years across, which is almost 5 times the distance from our Sun to the nearest star, Alpha Centauri. This cosmic seahorse should disappear completely within the next million years as more stars form in the cluster, which will slowly sweep away these structures with radiation and winds. Yes, the Tarantulus Nebula is special. It is huge and contains many interesting things. It serves as a cradle for the birth of new stars, and at the same time other stars end their lives in supernova explosions. This is a wealth of information, and invaluable information for astronomers. What would happen if a supernova exploded near Earth? There are actually 3 answers, none of them very comforting. But before we answer them, let's try to understand what a supernova birth is and why, even if they are very distant, they can harm all life. Thus, a supernova star or supernova flare is a star that rapidly increases its luminosity, followed by a relatively slow decay. A supernova is observed post facto, that is, after the event and its radiation reaches our eyes. A supernova occurs when there is a change in the center or core of a star. The change can take 2 forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is 2 stars orbiting the same point. One of the stars, White 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, neutron star, or black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers, a high density of up to 1 billion tons per cubic centimeter, and 2.5 times the mass of the Sun. After a supernova explosion, 2 types of neutron stars remain: pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars rotate on their axis at high speed, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, the probability of such an outcome is very high. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's a Betelgeuse star, 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation Orion continues to amaze with its mysterious behavior. At the end of 2020 it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse under gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes, sometimes people start doing something when it's too late, and it's better to prepare everything in advance when the last star leaves the station. But how to find what and how to prepare? Because our life is full of surprises. So if it's Betelgeuse, we shouldn't expect much danger. Yes, it would be wonderful, but the Earth would not be struck by a shock wave. The towers of heaven would not fall like matchsticks. The sea would not rise like a wall. And the inhabitants of the Earth would not burn like the last day. Apocalypse. I'm sorry, Thanos. So what will we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night, but it will not be like the second Sun. During the day, Betelgeuse will appear as a large bright spot, larger than an ordinary star but smaller than the Sun. At night, Betelgeuse will appear as a large bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months or up to a year. For another 2 years it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will be able to see the star's outer shell sooner. Fact, the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us, because neutrinos are strange particles that have nothing to do with the world. Look at your right leg. Trillions of neutrinos from the Sun pass through it every second. You don't see this shower because neutrinos have almost no effect on ordinary matter. Every few years, on average, one neutrino from these snowflakes will pull away a poorly anchored atom in your body. History shows that at least a dozen supernova flares in the distant past have survived us unscathed, and some were not far from us. Researchers have even been able to study the effects of these fires, not because it's scary, but because it's fun. Yes, there are some effects. In particular, geological layers of the Earth corresponding to specific time periods contain concentrations of rare isotopes that could only be produced by gamma radiation. However, the number of these isotopes is limited to a few atoms per ton of matter. No one would have found him unless he looked as special as Indiana Jones. To this we can add the increased concentration of nitrous oxide in the Antarctic ice. By the way, far from serious science, publications appear in the press about the possibility of the extinction of dinosaurs due to a nearby supernova. Alas, they have no scientific basis, since there are no traces of supernova explosions in several million years and in dinosaur bones. But those supernovae were far away, so we're still here. What would happen if a supernova occurred in the near future? To begin with, it is good to understand what is close and what is far on the interstellar scale. Our nearest star, Proxima Centauri, is 100 times dimmer than the red Derby Sun. It's about 4 light-years away, and in any case, this star doesn't threaten us with a supernova, no matter how angry you are. The components of the same system are located a little further away, and stars such as Alpha, Centauri, and our Sun will not be able to complete their evolution in such a spectacular way. We had to look for heavy stars, but none of the ones around the Sun. Even the bright Procyon Alpha Minor is 1.5 times larger than the Sun. we are interested in stars 8 solar masses and heavier. They end the evolution with a celebration and fireworks. And one. In front of you is the double star IR Pegasus, located 150 light-years away, which is 4 times closer than Betelgeuse. None of the stars in this system can produce a supernova flash, but working together it can. IK. One of the stars in the Pegasus system is the white dwarf. The other has reached the stage of becoming a red giant. Over time, the evil dwarf begins to attach the upper layers of the giant to itself, increasing its mass. After reaching a certain mass, the white dwarf has a chance to go supernova, and they should take advantage of it. But by then, the IK Pegasus system will be at a safe distance away from the Sun rapidly. However, if it happened now, it wouldn't be long before we felt its effects. One day we will see lights comparable to the Sun in the sky. For the Sun and the supernova to be on opposite sides of the Earth, the planet may not have any nights for a month or two. The visible light and heat rays from the supernova will cause a significant rise in temperature on the planet, albeit temporarily, and the radiation background would increase several times, which would put each Earth in a long mission to the ISS under astronaut conditions. But still, the inhabitants of our planet will be protected from the direct radiation of the supernova. For a while, earthworms will avoid bright light, stay indoors and play Tetris, go outdoors only when necessary, and cover their face and hands with masks and gloves. These theoretical considerations are not meant to prepare people to face another quarantine. However, let's imagine that the supernova exploded only 10 light-years away. Here, the results would be catastrophic. The flash also forms radioactive iron that can cause the destruction of the ozone layer and the penetration of dangerous ultraviolet rays into the planet, which will cause the extinction of all life on the planet. Bunker will be given some time, but this too will pass. And yet we can be sure that supernova diseases do not pose a threat to humanity. The risk of giant meteorite impacts, global pandemics, climate collapse, and nuclear war is greater. Yes, there is a lot of fear in our society, sometimes unfounded and unfounded. Fear is the strongest ray that destroys us more than the strongest religion. So we would fear in our life, at least not fearing one beautiful universal spectacle, the supernova star. Consider our favorite gold. Its nucleus consists of 79 positive protons, so gold must spin at more than half the speed of light to keep electrons from falling inside. This makes them more massive and pulls them into narrower orbits with lower energy. In this configuration, the electrons do not reflect blue light, thus giving gold jewelry its characteristic glow. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light to avoid collisions with the nucleus and violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let this be a ball of particles, and the elements can live up to about 173. These outliers may be atoms, but like strange creatures that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126 and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments but also by analyzing the distribution of various elements in nature. By distribution you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in the nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to the magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron, 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, neutron and proton shells are formed in the nucleus of an atom. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a superelement with a twice magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, cannot be predicted. Another area of stable isotopes is expected to be atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons it will be difficult to study them directly, because you can quickly break down, adding to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerates and collides with a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom, because less than 10/trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with high gravity, constant or changing temperature, new elements of matter can not only fill the table abundantly, but also reach a new level unknown to us. Yes, it is possible that black holes are composed of a complete set or nearly complete set of primordial particles that decay into energy, perhaps an indescribably fantastic conglomerate. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states, and these energies and forces of modern physics are known. But the combination of these energies could create something that is currently unknown to science. The cosmos beckons with its countless mysteries, challenging our understanding and igniting our imagination. From the mysterious depths of black holes to the enigmatic behavior of distant galaxies, the cosmos abounds with phenomena that defy simple explanation. Join us as we unravel the secrets of the universe, one cosmic mystery at a time. Beneath the thick and poisonous clouds of Venus lies an incredibly hostile environment, far from favorable to any form of life as we know it. Venus's atmosphere is composed mostly of carbon dioxide, and clouds of sulfuric acid cover the planet in a shroud. These clouds create such a strong greenhouse effect that the average surface temperature is about 800 degrees Fahrenheit, making it hotter than Mercury's surface despite being farther from the Sun. Atmospheric pressure on Venus is another major factor contributing to its inhospitable nature. At the surface, the pressure is about 90 times Earth's pressure, which is akin to being nearly a mile under the ocean. The immense pressure is capable of crushing any human-made spacecraft, making exploration extraordinarily difficult. The combination of extreme temperature and high pressure creates conditions that no known organism on Earth can survive. In addition, there is volcanic activity on the surface of Venus, which accounts for the harsh landscape. Scientists believe that many of these volcanoes may still be active, releasing additional gases and contributing to the thickness of the planet's atmosphere. The presence of volcanic plains and vast elevations adds to Venus's intrigue, revealing a planet shaped by powerful geologic forces. In recent years, scientists have even speculated about the possibility of microbial life in the upper atmosphere, where conditions are slightly less extreme. However, the harsh conditions on the surface, combined with clouds of sulfuric acid, make Venus virtually unsuitable for life of any complex form. The mysteries hidden beneath its clouds continue to mesmerize researchers, which has prompted further missions to explore this enigmatic planet. The idea of a ninth planet lurking in remote corners of our solar system has gained traction among astronomers in recent years, primarily due to the unusual orbits of some celestial objects in the Kuiper belt. Distant icy bodies exert a gravitational influence, suggesting the presence of an unseen giant planet. This hypothetical planet is often referred to as Planet 9 or sometimes Planet X, although no direct observations of it have yet been made. Planet 9 is believed to be much larger than Earth, perhaps several times its mass, and has a highly elliptical orbit that puts it well beyond the known planets. According to some models, it could be anywhere from 20 to 800 astronomical units away from the Sun, where 1 astronomical unit is the average distance from Earth to the Sun. This vast distance makes detecting a planet extremely challenging, as it may be relatively dim and distant, but its gravitational influence may be enough to affect the orbits of debris in the Kuiper belt. Interestingly, the search for the ninth planet has been the subject of considerable research and debate. Astronomers are using modern telescopes and computer modeling to study the potential location of this elusive planet. As data accumulates, researchers hope to pinpoint its location and eventually obtain a direct image of the ninth planet, which could shed light on our understanding of the formation and evolution of the solar system. Unraveling the mystery of the ninth planet may also spark discussions about the possibility of other undiscovered planets lurking in the far corners of our solar system. The dynamics of distant celestial objects hint at a rich and complex structure with many mysteries still waiting to be discovered. As new observations are made, the search for this mysterious planet continues to inspire scientists and astronomy enthusiasts alike. The hexagonal storm at Saturn's North Pole is one of the most intriguing and unique weather phenomena observed in our solar system. This striking hexagonal pattern, about 14,000 miles wide, has fascinated scientists since it was first discovered by the Voyager spacecraft in the 1980s. The stable shape of this massive storm raises questions about the complex dynamics of Saturn's atmosphere. The hexagon is believed to be the result of a complex interaction of atmospheric currents rather than a single storm. It is formed by the interaction of fast-moving winds in Saturn's atmosphere that create a standing wave pattern. Cold winds in Saturn's polar region blow at speeds of more than 150 miles per hour. These winds create a rotational effect combined with the planet's rapid rotation, resulting in a distinct geometric hexagonal shape. Researchers have used fluid dynamics experiments to reproduce this hexagonal structure in a laboratory setting. When they create a rotating system of fluids and introduce an obstacle into the flow, a hexagonal pattern emerges. This suggests that the hexagon on Saturn is stabilized by the hydrodynamics underlying the planet's atmosphere. Seasonal changes also play a role, as fluctuations in sunlight and temperature affect wind patterns and can change the appearance or intensity of a hexagonal storm. The hexagon is not just static. It exhibits change and dynamics by showing the formation and movement of small storms along its edges. Remarkably, it has persisted for decades, if not longer, indicating a robust atmospheric system that continues to intrigue scientists. Understanding the hexagonal storm not only reveals the complexity of Saturn's weather, but also deepens our knowledge of hydrodynamics on a planetary scale. Uranus is unique among the planets in our solar system due to its sharp tilt, which causes it to spin on its side. While most planets have an axial tilt of less than 30 degrees relative to their orbits around the Sun, Uranus boasts an inclination of about 98 degrees. This peculiar orientation sets it apart from others and produces a distinct set of seasonal patterns and atmospheric behavior. The leading theory for Uranus's unusual tilt suggests a massive collision with one or more celestial bodies during its formative years. Such a significant impact could have knocked the planet off its original axis, resulting in the extreme tilt observed today. This theory is consistent with the notion that major collisions were common in the early solar system, which could easily alter the planet's rotation axes. In addition to its axial tilt, Uranus's rotation is also remarkable because it rotates very slowly around its axis, making one revolution in about 17 hours. As a result, at each pole, long periods of sunshine are followed by prolonged darkness, resulting in extreme seasonal variations. Uranus's orientation relative to its orbit allows one hemisphere to be constantly exposed to sunlight for long periods of time, while the other hemisphere remains in darkness. In addition, Uranus's unusual tilt affects the dynamics of its atmosphere. The planet's weather is characterized by high-velocity winds and shifting clouds, providing an intriguing insight into the planet's complex processes. Researchers continue to study Uranus, and the mysteries surrounding its tilt and rotation provide valuable clues about the formation of the planets and the turbulent history of our solar system. The origin of Mars's moons, Phobos and Deimos, has intrigued scientists for years, generating various theories about how these small celestial bodies came to orbit the red planet. Phobos, the larger of the two moons, and Deimos are irregularly shaped and relatively small compared to Earth's moons, 14 and 8 miles in diameter respectively. The unusual characteristics of these objects suggest to astronomers that they may not be native to Mars, but captured asteroids from the asteroid belt. The most widely supported hypothesis suggests that Phobos and Deimos are remnants of a larger population of rocky bodies in the asteroid belt. It is hypothesized that early in the history of the solar system, gravitational interactions may have drawn these objects to Mars, allowing them to become satellites of the planet. The close similarities between the composition of Phobos and certain types of asteroids, particularly carbonaceous chondrites, further supports this capture theory. Another compelling aspect in favor of their origin is the low density of both moons, indicating their composition is rich in carbonaceous materials and possibly ice. This matches the characteristics of some asteroids, hinting that Phobos and Deimos formed somewhere in the solar system before falling under the gravitational pull of Mars. Their irregular shape and the significant craters they display also suggest a collision history comparable to that of many other small bodies in the solar system. However, there are alternative theories, including the possibility that they formed in situ from debris ejected into Mars's orbit as a result of collisions with the planet itself. Despite the various hypotheses, The nature of Phobos and Deimos remains the subject of ongoing research. Future missions targeting these moons may yield new insights that could help shed light on the intriguing history of Mars and its unique satellites. Beneath Europa's thick icy crust lies one of the most compelling candidates for potential extraterrestrial life in our solar system. This moon of Jupiter is believed to possess a subsurface ocean hidden beneath an impressive layer of ice several miles thick. Scientists estimate that this ocean may contain more than twice as much water as Earth's, making Europa a particularly interesting object to study. The presence of liquid water is a critical factor in the search for extraterrestrial life. Water is often considered a universal solvent essential for biochemical processes. The ocean beneath Europa's icy surface is thought to be in contact with the Moon's rocky mantle, allowing chemical exchanges that could create a suitable environment for life. Just as hydrothermal vents on Earth give rise to diverse ecosystems, scientists hypothesize that similar processes may occur on Europa's seafloor, where mineral-rich water could nourish potential microbial life forms. Data from instruments such as Galileo and observations from the Hubble Space Telescope show plumes of water vapor erupting from Europa's surface. These plumes provide tantalizing clues about the composition of the subsurface ocean, hinting at the possibility of organic molecules. Analyzing these features could provide more information about the Moon's potential suitability for life without the need to drill for ice. Future missions, such as NASA's Europa Clipper, aim to study the Moon's icy crust and more thoroughly assess its potential for life. This research could unlock the secrets of Europa's hidden ocean and explore the conditions that may allow life to thrive in an environment vastly different from Earth's. The idea of detecting life beneath Europa's ice is fascinating to scientists and humanity, raising profound questions about our place in the universe. Mercury's composition is strikingly different from that of other terrestrial planets. Notably, the Moon has an unusually large iron core, comprising about 70% of the planet's total mass. This disproportionate presence of iron has puzzled scientists and led researchers to delve deeper into the formation of Mercury and the processes that shaped it in the early solar system. According to one prevailing theory, Mercury's large iron core is the result of a massive impact during its formation. During the formation of the planets in our solar system, there were numerous collisions of protoplanetary material. As a result of a violent collision, much of Mercury's outer silicate mantle may have been blown away, leaving behind much of the dense iron core. The remaining mantle is relatively thin compared to the mantles of other planets, emphasizing the dominant role of the core in Mercury's overall structure. Another factor contributing to Mercury's formation may be the planet's proximity to the Sun. As the closest planet, Mercury experienced higher temperatures during its formation, which may have affected the differentiation of materials. Under the action of heat, lighter compounds may have vaporized or been pushed outward, while denser ions subsided to form the core. This differentiation process may have been more extreme for Mercury than for other terrestrial planets such as Earth, Venus, and Mars. In addition, Mercury's evolution is also influenced by its geologic history. Traces of volcanic activity have been found on the planet, and it is speculated that it may have occurred after the core was formed. Understanding Mercury's current structure, including its core and mantle, gives us valuable clues about the formation of planets and the unique conditions that can lead to such distinctive characteristics of celestial bodies. As we learn more about Mercury through current and future missions, the enigmatic nature of its large iron core is becoming increasingly clear, deepening our understanding of the history of the solar system. The mysterious spokes observed in Saturn's rings are a fascinating feature that has puzzled scientists since it was first discovered in the 1980s by the Voyager spacecraft. These spokes appear as radial structures that can span thousands of kilometers and appear to change in intensity and shape over time. Their transient nature, combined with their striking appearance, makes them one of the most intriguing phenomena associated with Saturn's iconic rings. The prevailing theory for the formation of these spokes suggests that they result from the interaction of charged dust particles inside the rings and Saturn's magnetic field. The spokes are thought to be made up of small particles that are electrically charged by sunlight and interaction with the planet's magnetic field. The charging process causes particles to become suspended in the rings, resulting in visible features as they interact with various magnetic forces and gravitational influences. Observations have shown that these spokes tend to appear more clearly when Saturn is close to the equinox, the time when the Sun casts a shadow on the rings. This seasonal effect affects the brightness and visibility of the spokes, suggesting that they may be affected by changes in lighting conditions. When Saturn's rings are illuminated in a certain way, the charged particles can align or cluster together, creating the striking linear patterns we observe. Despite ongoing research, many aspects of spicules remain elusive, leading to various hypotheses about their formation and behavior. Some scientists speculate that the spokes may be related to the dynamics of the ring particles themselves or even the gravitational interaction of nearby moons. As new missions and improved observational techniques continue to yield data about Saturn and its rings, we will be able to better understand these fascinating and mysterious structures in one of the most fascinating systems in our solar system. The formation of Pluto and its largest moon, Charon, is a fascinating story that has intrigued scientists for decades. Both celestial bodies are in the Kuiper Belt, a region beyond Neptune inhabited by many small icy objects. The prevailing theory suggests that Pluto and Charon formed from the same primordial material as other bodies in the Kuiper Belt at the dawn of our solar system. According to this model, Pluto and Charon likely formed through a process called accretion. According to this scenario, dust and ice particles condensed in the cold outer regions of the solar system, gradually forming larger bodies. By colliding and interlocking with each other, these particles formed large planetesimals. Over time, gravity continued to cause these objects to collide and merge, leading to the formation of Pluto. This process would also have allowed smaller bodies to combine to form Charon, which is unusually large compared to Pluto, making it unique among the large moons of our solar system. However, the relationship between Pluto and Charon is particularly intriguing. The size ratio of the two planets, where Charon's diameter is about half that of Pluto, suggests that a significant collision occurred during their formation. Some scientists speculate that Charon may have formed after a massive collision knocked a significant amount of material off Pluto. This debris then merged into Charon, resulting in the synchronized relationship we see today. The two bodies are tidally locked to each other and always show the same face. Further studies of the Pluto-Charon system, including data obtained in 2015 by NASA's New Horizons spacecraft, have provided valuable insights into their composition and geology, revealing a complex history. Understanding their formation not only sheds light on the dynamics of the Kuiper Belt, but also provides a broader view of the processes that shape the solar system as a whole. Through ongoing research, we continue to learn about these distant worlds and the cosmic events that brought them into existence. Bright spots on the dwarf planet Ceres are one of the most intriguing features observed in our solar system. Ceres, located in the asteroid belt between Mars and Jupiter, has attracted the attention of scientists since NASA's Dawn spacecraft began its mission to study the dwarf planet in 2015. The brightest of these bright spots are located in an area called the Okator crater and have sparked much interest in their composition and origin. These bright spots are thought to be composed primarily of sodium carbonate, a type of salt, as well as other reflective materials. Brightness is likely due to how sunlight interacts with the surface, emphasizing how differently bright spots reflect light compared to the surrounding terrain. Spectroscopic analysis has revealed the presence of certain salts, suggesting that these materials may have originated from saltwater beneath Ceres's surface. When liquid water rich in these salts rose up and evaporated, it left behind the bright remnants we observe. The presence of these bright spots indicates that cryovolcanism, or cold volcanism, may have occurred on Ceres in the past. This geologic process involves the eruption of icy materials rather than molten rock. The idea is that warm salt water may have penetrated through cracks in Ceres' crust, leading to the formation of the bright deposits. Continued study of these areas has revealed several features, such as domes and mounds, that may indicate past geologic activity. Understanding the bright spots on Ceres is important for several reasons. Not only do they provide insight into the dwarf planet's geologic history, but they also have implications for the broader study of icy bodies in our solar system. The presence of water, even in frozen or salty form, raises questions about the possibility of past habitability or the existence of life in such extreme conditions. While research continues, Ceres's bright spots remain the focus of researchers, revealing the complexity and richness of this intriguing celestial body. Inside the event horizon of a black hole is one of the most mysterious and extreme environments in the universe. The event horizon represents a boundary beyond which nothing can escape the formidable gravitational pull of a black hole, including light. Beyond this threshold, the concept of location and time undergoes profound changes due to the intense action of gravitational forces. It is believed that when anything crosses the event horizon, it is inexorably drawn toward the singularity, the core of a black hole, where density becomes infinite and the known laws of physics collapse. At this point, space and time lose their usual meanings. According to current theories, all paths, regardless of direction, eventually lead to the singularity, creating a one-way journey for anything that dares to approach it. This irreversibility is what defines the event horizon as the point of no return. The environment within the event horizon is also characterized by extreme tidal forces. Near the singularity, the gravitational attraction differs dramatically between the parts of the object closer to the center of the black hole and those farther away. This discrepancy can lead to a process known as spaghettization, where objects are stretched vertically and compressed horizontally, resembling strands of spaghetti. This effect occurs due to the curvature of spacetime caused by the enormous gravity of a black hole. Given the current state of physics and our understanding of black holes, much about what happens inside the event horizon remains speculative. As scientists continue to explore the interplay between general relativity and quantum mechanics, questions about the nature of spacetime, the conservation of information, and the fate of matter and energy subjected to these extreme conditions will remain relevant. The quest to understand black holes and what's inside them is not only a journey into the depths of these mysterious objects, but also a deep exploration of the fabric of the universe itself. The formation of supermassive black holes at the centers of galaxies is a complex process that remains an active area of research in astrophysics. These giants can reach masses millions or even billions of times that of our Sun, and their presence affects the dynamics and evolution of the galaxies in which they reside. Understanding how they are formed involves several interrelated theories. One of the leading hypotheses suggests that supermassive black holes are formed by the merger of smaller black holes and dense star clusters. In the early universe, the rapid collapse of massive clouds of gas and dust may have led to the formation of many small black holes. As these black holes drift through the surrounding matter, accreting gas in the process, some of them may eventually coalesce through gravitational interactions to form larger black holes over time. Another important factor is the role of the environment in which galaxies evolve. In the dense centers of galaxies, interactions between stars and gas clouds can lead to more efficient accretion of material onto these black holes. As they accumulate mass, they can emit enormous amounts of energy, which is often seen in the form of quasars, the incredibly bright and energetic centers of active galaxies. Intense luminosity occurs when gas spirals into a black hole, resulting in extremely high temperatures and radiation. The growth of supermassive black holes can also be linked to the overall evolution of galaxies. Mergers between galaxies, common throughout cosmic history, can involve gas and stars in the central regions, enhancing the growth of existing black holes. Such interactions not only increase their mass, but also determine the structure and dynamics of galaxies. The balance between the growth of black holes and the galactic environment plays an important role in the evolution of both. Despite these theories, many details about the formation of supermassive black holes remain unresolved. Research continues to investigate how these huge entities managed to form so quickly after the Big Bang, and how they interact with their host galaxies over cosmic time. Ongoing observations with modern telescopes are revealing more about the nature and formation processes of supermassive black holes and providing a deeper understanding of the interactions between black holes and the galaxies they inhabit. Fast radio bursts, known as FRBs, are high-energy and extremely short bursts of radio waves that have attracted the attention of astronomers and astrophysicists around the world. First detected in 2007, these mysterious signals last only a few milliseconds, but emit an astonishing amount of energy equivalent to what the Sun radiates for 10,000 years. Understanding their origin and mechanisms has become an important area of research in astrophysics. The exact cause of fast radio bursts remains unclear, leading to many theories about their origin. One well-known hypothesis suggests that FRBs may arise from extraordinary cosmic events such as neutron star collapse or neutron star mergers, when extreme gravitational and magnetic forces generate intense bursts of energy. Another possibility is the interaction of magnetars, highly magnetic and rapidly spinning neutron stars, with their environment. These magnetar bursts can produce powerful bursts of radiation that can potentially manifest as FRBs. Moreover, some of the more exotic theories suggest that FRBs may be related to processes in the early universe, such as the formation of black holes or even signals from advanced extraterrestrial civilizations. Although the latter idea is tantalizing, the scientific community has tended to focus on natural astrophysical phenomena as the sources of these radio bursts. Recent advances in observational technology have allowed astronomers to determine whether some FRBs belong to specific galaxies, providing clues to their origin. Notably, some FRBs are recurrent, suggesting that they are associated with localized, energetic astrophysical sources. The ongoing study of fast radio bursts continues to yield exciting discoveries, bringing us closer to understanding these elusive cosmic phenomena. While scientists work to unravel their mysteries, FRBs contribute to our knowledge of the universe and the many dynamic processes occurring beyond our planet. Magnetars are an interesting class of neutron stars known for their incredibly powerful magnetic fields, whose strength can exceed 1 trillion Gauss, making them the most magnetically powerful objects in the universe. The origin of these huge magnetic fields is rooted in the processes that occur during the formation of neutron stars, as well as the unique properties of their dense and compact matter. When a massive star exhausts its nuclear fuel, it undergoes a supernova explosion, collapsing under its own gravity. The core can shrink into a neutron star, a remnant of the original stellar core where neutrons are packed tightly together by extreme gravitational forces. When a collapse occurs, several important factors contribute to the formation of an intense magnetic field. According to one leading theory, during the rapid rotation of a collapsing star, the conservation of angular momentum leads to a strengthening of the existing magnetic field. The dense matter of a neutron star, combined with the intense rotation and factors associated with a supernova explosion, can lead to a dynamo effect. As the star rotates, it generates a magnetic field, the strength of which can increase dramatically. Furthermore, the conditions inside a neutron star are extreme. At such high densities, matter behaves differently than under normal conditions, allowing for complex interactions that contribute to the generation of the magnetic field. The presence of superfluid neutrons and related phenomena can also affect the structure of the magnetic field. In a magnetar, these fields can occur rapidly, resulting in a core that can maintain and preserve an extremely strong magnetic field. In addition, the enormous energy associated with the magnetars can cause the magnetic field to gradually decay or rearrange over time. As they age, magnetars can periodically release bursts of energy or flares due to magnetic field reconfiguration, releasing vast amounts of energy and emitting radiation in multiple wavelength ranges. This unique behavior reveals not only the potential of magnetars, but also their complex evolution and interactions with their environment. Ongoing studies of these stellar phenomena allow us to better understand the physics behind their powerful magnetic fields and the implications of their study in the universe. Dark energy is the mysterious force that pervades the universe and is responsible for its accelerated expansion. Discovered in the late 20th century through observations of distant supernovae, scientists discovered that the universe is not only expanding, but doing so at an ever-increasing rate. This discovery has sparked increased interest and research into what dark energy actually is. About 70% of the universe is thought to be composed of dark energy. Despite the prevalence of this phenomenon, its exact nature remains elusive. One leading explanation states that dark energy is a property of space itself. As space expands, more and more dark energy appears, creating a feedback loop that contributes to further acceleration. This concept is rooted in Einstein's general theory of relativity, which allows for the existence of a cosmological constant, a term that can explain the density of energy in empty space. Alternative theories suggest that dark energy may be a dynamic field that changes over time, affecting acceleration at different epochs in cosmic history. Some scientists speculate that it may be related to changes in gravity on cosmic scales. Each of these theories attempts to reconcile the observations with our understanding of fundamental physics, but none has yet provided a definitive explanation for the phenomenon. The study of dark energy represents one of the major challenges of modern cosmology. Its discovery has raised more questions than answers, prompting scientists to develop new observational methods and theoretical models. Unraveling the secrets of dark energy may not only help us understand the fate of the universe, but also deepen our understanding of the fundamental laws governing cosmic evolution. Quasars are some of the brightest objects in the universe, often outshining entire galaxies. The huge release of energy results from activity around supermassive black holes located at the centers of distant galaxies. When matter is spiraled into black holes, it forms an accretion disk composed of gas, dust, and other materials that become incredibly hot due to friction and gravitational forces. This process converts potential energy into thermal energy, resulting in extraordinary levels of light and radiation. The temperature in an accretion disk can reach millions of degrees, causing the matter to emit powerful electromagnetic radiation across the entire spectrum, including visible light, ultraviolet radiation, and X-rays. The energy emitted by quasars can reach levels 1,000 times the energy of all the stars in a typical galaxy combined. It is because of this prohibitive brightness that quasars can be detected at great distances, allowing astronomers to observe them from billions of light-years away. Another contribution to the energy production in quasars comes from relativistic jets emitted along the black hole's axis of rotation. These jets are composed of charged particles that are accelerated to near the speed of light, releasing additional energy in the form of radiation. These jets can propagate over vast distances, sometimes thousands of light-years, and affect their host galaxies by transferring energy and momentum to surrounding matter. Studying quasars expands our understanding of the evolution of galaxies and the universe itself. By studying their properties, including their brightness and spectrum, astronomers gain insight into the conditions of the early universe and the processes that govern the formation and growth of black holes. Quasars serve as cosmic beacons, illuminating the depths of cosmic history and the complexity of the forces driving the evolution of the universe. Gamma-ray bursts are the most powerful explosions observed in the universe, releasing huge amounts of energy in the form of gamma rays, which are the most energetic form of light. These unusual phenomena are thought to occur during the death of massive stars, or when compact objects such as neutron stars or black holes merge. In the case of massive stars, when they exhaust their nuclear fuel, they can collapse under their own gravity, leading to a catastrophic implosion and subsequent supernova explosion. If a core collapse is accompanied by powerful jets of matter, these jets can produce the gamma rays that characterize the outburst. When a neutron star merges with another neutron star or black hole, it can also result in a gamma ray burst. In this scenario, the merger process releases enormous gravitational energy and can lead to the formation of a rapidly rotating black hole surrounded by an accretion disk. When matter is pulled into a black hole, powerful jets are ejected along its axis of rotation. If these jets are directed toward Earth, we observe them in the form of a gamma-ray burst. Gamma-ray bursts fall into two main categories: long-period bursts, lasting from a couple of seconds to several minutes, and short-period bursts, usually lasting less than 2 seconds. Long-duration bursts are mostly associated with the death of massive stars, while short-period bursts are usually associated with the merger of compact objects. This distinction helps scientists understand the different environments and conditions that lead to these explosive phenomena. The energy released in a gamma-ray burst can be staggering, often exceeding the total radiation from our Sun over its lifetime in just a few seconds. These bursts are so bright that they can be observed over vast cosmic distances, allowing astronomers to study these phenomena and gain insight into the extreme processes occurring in the universe. Understanding gamma-ray bursts not only sheds light on stellar evolution and black hole behavior, but also challenges our understanding of fundamental physics in the extreme. Binary star systems, consisting of two stars gravitationally bound together, often form from the same dense region of gas and dust in a molecular cloud. When parts of a cloud break apart under gravity, they can break up into smaller clumps, each of which begins the star formation process. If two such clumps are close enough, they eventually form stars orbiting each other. Initial conditions play a crucial role in determining the properties and evolution of a binary system. Once a binary system is formed, its evolution can take different paths depending on what happens. Their evolution can follow different paths depending on the masses of the stars and their orbital characteristics. If two stars have similar masses, they may simultaneously undergo similar stages of evolution, leading to complex interactions. As they evolve, they may expand and become red giants. If the stars are close enough, their outer layers can begin to transfer mass to each other, leading to phenomena such as mass exchange or even the formation of additional structures such as accretion disks around the companion star. In cases where one of the stars becomes much more massive than the other, it may become a supernova, leaving behind a neutron star or black hole. A companion star will continue its evolution independently. At these moments, the dynamics of the system can change significantly, especially if the supernova remnants gravitationally interact with the companion star. This can often lead to scenarios such as the formation of a binary neutron star system, or a pair of neutron stars with a black hole, both of which can emit gravitational waves as they spiral towards each other. The study of binary star systems is essential to understanding stellar evolution and the mechanics of the universe. By observing these systems, astronomers can collect data on stellar masses, luminosities, and ages, contributing to broader models of how stars form, evolve, and ultimately affect their galactic environment. This study not only expands our knowledge of the life cycles of stars, but also informs theories about the distribution of matter in the universe. Cosmic rays are high-energy particles coming from space, and those with ultra-high energy are particularly intriguing to scientists. The energy of these cosmic rays can exceed 1 quintillion electron volts, which is millions of times more energetic than particles created in man-made gas pedals, such as the Large Hadron Collider. The origin of these ultra-high-energy cosmic rays remains the subject of active research, with several potential sources being investigated. According to one leading hypothesis, ultra-high-energy cosmic rays emanate from supermassive black holes located at the centers of active galaxies. These regions contain vast amounts of energy and can accelerate protons and heavier nuclei to extreme speeds through processes such as shock waves and magnetic fields in the vicinity of a black hole. When charged particles travel through intergalactic space and interact with photons from the cosmic microwave background, they can reach energies far beyond what is currently achievable in the laboratory. Another suspected source of these high-energy particles are gamma-ray bursts, which are the most energetic events in the universe. During these explosive episodes, energy is concentrated in a very limited region capable of accelerating particles to ultra-high energies. In addition, certain types of supernova remnants and neutron star mergers are also considered potential sources because they can create the necessary conditions for particle acceleration. Although there are suspected sources, pinpointing the exact origin of ultra-high energy cosmic rays is difficult because of their trajectory. They are affected by the magnetic fields present in interstellar and intergalactic space. As a result, it can be almost impossible to trace their source. Advanced observational techniques using vast arrays of air showers and neutrino detectors aim to achieve a clearer understanding of these cosmic rays, which could ultimately unlock the mysteries of extreme astrophysical processes in the universe. The answers to these questions can help deepen our understanding of the fundamental physics and nature of the cosmos on the largest scales. Type Ia supernovae are a spectacular and predictable type of explosion, often used by astronomers as cosmic yardsticks to measure distances in the universe. The origin of these events can be traced to the example of white dwarfs, which are the remnants of stars that have exhausted their nuclear fuel. A white dwarf is composed mostly of carbon and oxygen, and it is kept from gravitational collapse by electron degeneracy pressure. For a white dwarf to ignite in a type Ia supernova, it must undergo a process called accretion, during which it gains mass from a companion star in a binary system. This companion could be either another ordinary star or another white dwarf. As a white dwarf accumulates matter, particularly hydrogen and helium, its mass gradually increases. According to an established threshold known as the Chandrasekhar limit, when the mass of a white dwarf approaches about 1.4 times the mass of the Sun, the temperature and pressure in its core become high enough to initiate nuclear fusion. Once fusion begins, it triggers a rapid, uncontrolled process that converts carbon and oxygen into heavier elements. This reaction releases a huge amount of energy, and the white dwarf explodes in a violent flash. The explosion is not a typical stellar detonation. Instead, thermonuclear acceleration occurs. This means that thermonuclear reactions proceed at an accelerated rate on the chain reaction principle, resulting in a cataclysmic release of energy that completely destroys the white dwarf and produces huge amounts of radioactive material. The aftermath of a type Ia supernova causes the heavy elements to disperse into space, enriching the surrounding interstellar medium. These elements contribute to the formation of new stars, planets, and eventually life itself. The predictable luminosity of type Ia supernovae, due to the constant mass of the exploding white dwarfs, allows astronomers to use them to measure cosmic distances and study the expansion of the universe. Understanding this process deepens our understanding of stellar evolution and the life cycle of matter in the cosmos. Concepts from biology, particularly the idea of emergentism, provide a fascinating lens through which to explore the origin of the universe. Emergentism refers to the process by which complex systems and patterns emerge from the interaction of simpler components. This principle can shed light on our understanding of how the universe evolved from an incredibly dense and homogeneous state to the vast and complex cosmos we observe today. In the context of cosmology, the early universe is often described as being in a state of high energy and homogeneity. As the universe expanded and cooled, small fluctuations occurred at quantum levels, resulting in tiny changes in density. These tiny differences can be compared to the components of a biological system, where the interaction of individual components leads to the emergence of larger, more holistic structures. The concept of emergence helps explain how such tiny fluctuations eventually led to the formation of galaxies, stars, and planetary systems, demonstrating the transition from simplicity to complexity over time. In addition, understanding emergence in biology can help in the study of self-organization in the universe. Just as biological systems such as flocks of birds or cellular structures can create complex patterns without central control, the universe exhibits self-organizing behavior at cosmic scales. Gravitational interactions between matter can lead to the formation of large structures, such as galaxies and galaxy clusters, out of primordial chaos. This process emphasizes how fundamental forces and simple interactions can give rise to complex structures and systems in both biology and cosmology. In addition, concepts of emergence in biology raise intriguing questions about the nature of life itself and its place in the universe. If we consider the universe as a complex system, the emergence of life can be seen as one of its many outcomes. The study of complex adaptive systems in biology, including ecosystems and evolutionary processes, can provide insights into how the emergence of life reflects basic physical laws and cosmic dynamics. Moreover, interdisciplinary approaches that combine insights from biology, physics, and philosophy can expand our understanding of both the origin of the universe and the emergence of consciousness. By studying how individual and collective behavior emerges in different contexts, scientists will be able to better understand how conscious beings are connected to the cosmos, and how the universe itself may contain forms of information processing or consciousness at different scales. Concepts of the emergence of life in biology enrich our understanding of the origin of the universe by emphasizing the complex interplay of fundamental processes that lead to the formation of complex structures and systems. This view promotes a more integrated view of the cosmos and life's place in it, encouraging research that spans across disciplines to deepen our understanding of being. Neuroscience can provide significant insight into our ability to comprehend abstract concepts such as nothingness and the early universe by studying how the brain processes complex ideas, shapes understanding, and interprets experience. While people are trying to make sense of these deep philosophical and scientific concepts, neuroscience offers explanations for the cognitive mechanisms involved. One key aspect of this research is how the brain conceptualizes the idea of nothingness, a concept that challenges our traditional understanding of existence. Neuroscientific research shows that the human brain does not tend to comprehend the absence of something. Instead, we tend to fill in the gaps with context-rich interpretations based on sensory experience. This tendency is rooted in our evolutionary need to navigate the physical world that shapes our perceptions and cognitive frameworks. The brain's dependence on context means that thinking about the concept of non-existence often leads to abstract thinking, which can cause feelings of uncertainty or discomfort. In addition, understanding the neural basis of abstract thinking may shed light on how humans imagine the early universe, which encompasses vast scales of time and space, as well as conditions that seem completely alien to human experience. Neuroscience has identified brain regions involved in reasoning, imagination, and spatial cognition, such as the prefrontal cortex and parietal lobes. These areas are engaged when people try to build mental models of cosmic phenomena or visualize timescales beyond everyday experience. The brain's ability to create and manipulate abstract representations allows us to formulate hypotheses and ideas about the origin of the universe, even if these concepts remain beyond direct observation. Furthermore, the concept of cognitive elasticity plays a key role in how we adapt our understanding of complex topics such as the early universe. Neuroplasticity, the brain's ability to reorganize itself in response to learning and experience, makes it easier to incorporate new scientific knowledge into existing mental frameworks. As our knowledge of physics and cosmology expands, humans may change their view of the universe and its initial conditions. As a result, people attempt to construct mental models of cosmic phenomena or visualize timescales beyond everyday experience. In addition, exploring the philosophical aspects of neuroscience can shed light on how concepts of nothingness and the origin of the universe intersect with existential questions about consciousness, perception, and reality. This research can lead to deeper insights into the human condition and existential experience, further enriching the debate on the nature of existence and non-existence. Neuroscience offers valuable insights into our ability to comprehend nothingness and the early universe by studying how the brain processes abstract concepts, builds mental models, and adapts to new knowledge. This understanding links cognitive science to philosophical inquiry and provides a framework for exploring the nature of existence, ultimately increasing our appreciation of the deep mysteries of the cosmos. Psychological concepts of perception can significantly influence our theories about states before the Big Bang, shaping how we interpret and conceptualize the origin of the universe. Perception, which underlies human cognition, not only dictates how we perceive reality, but also influences the framework we use to understand abstract concepts that lie beyond direct observation, such as conditions before the Big Bang. One key psychological aspect is that human perception is limited to sensory experience. Our brains evolved to interpret information based on direct physical encounters and relationships in a three-dimensional world. When theorizing about the state before the Big Bang, which may involve measurements or conditions beyond our sensory limitations, scientists must rely on abstract reasoning and analogies. This dependence may affect the formulation of theories about the early universe as complex phenomena are described in more comprehensible terms, potentially leading to interpretations closer to our perceptual experience rather than strictly conforming to scientific rigor. In addition, cognitive biases determine how scientists treat abstract cosmological concepts. For example, the human tendency to think teleologically can affect our interpretations of the state before the Big Bang. This bias can lead us to attribute purpose or direction to the formation of the universe, which may not reflect underlying physical principles. Such biases can shape theoretical narratives and influence the acceptance of certain models over others, thereby influencing the direction of research and inquiry in cosmology. Moreover, our understanding of ambiguity and uncertainty from a psychological perspective plays a crucial role in interpreting theories that predate the Big Bang. Human cognition often struggles with ambiguity, which leads to attempts to create order out of chaotic or uncertain concepts. In the context of the early universe, where initial conditions may be poorly understood or radically different from our everyday experience, this tendency can lead to a penchant for deterministic models that promise clarity. Advances in theoretical physics require balancing this desire for understanding with the uncertainty inherent in such complex concepts. In addition, psychological perceptions can also influence the collaborative nature of scientific research. How theories about the pre-Big Bang state are communicated and understood in the scientific community can affect the collaboration and synthesis of ideas. The influence of group dynamics, social approval, and consensus can lead to the normalization of certain theories and the marginalization of alternative viewpoints. This dynamic is crucial because it shapes the research landscape and influences which theories take the lead. Psychological conceptions of perception significantly influence theories about pre-Big Bang states, shaping our interpretations of complex and abstract phenomena. The limitations of human cognition, cognitive biases, reactions to uncertainty, and collaborative dynamics all contribute to the framework through which we understand the origin of the universe and ultimately influence the focus of research in cosmology. Parallels between cosmic and biological evolution reveal surprising similarities in the processes that govern the development of complexity in both the universe and life on Earth. By examining these common characteristics, we can further understand how complex structures emerge in very different contexts. One of the most striking parallels is the idea of gradual change through incremental steps. In cosmic evolution, the universe began with the Big Bang and has since expanded, cooled, and evolved through various stages, from the formation of subatomic particles to the creation of stars, galaxies, and eventually complex structures such as planetary systems. Similarly, biological evolution occurs through the gradual change of species over time under the influence of genetic mutations and natural selection. Both processes illustrate the path from simple beginnings to increasingly complex forms, emphasizing that complexity can emerge incrementally from simpler components. Another significant parallel is the role of randomness and chaos in both cosmic and biological contexts. In the universe, quantum fluctuations in the early universe can affect the distribution of matter, leading to the formation of large-scale structures and determining the paths of cosmic evolution. In biology, genetic mutations occur randomly and can create variations among organisms, some of which may confer advantages under certain conditions. In both scenarios, randomness introduces variability, and underlying laws, such as gravity in cosmology and natural selection in biology, help guide the trajectory of evolution toward more organized states. Moreover, both cosmic and biological evolution involve processes of self-organization. In space, gravitational forces lead to the self-organization of stars and galaxies as matter coalesces under gravity to form complex structures. In biology, self-organization is evident in the development of complex multicellular organisms from simpler cellular aggregates, where individual cells combine to form tissues and systems through concerted interactions. Both systems demonstrate how interactions between simpler components can lead to emergent properties that cannot be predicted based on components alone. In addition, both fields demonstrate the concept of interdependence and interconnectedness. In the universe, galaxies interact gravitationally to influence each other's evolution, and stars, through nuclear fusion, produce elements that become the building blocks for planets and eventually life itself. Similarly, in biological ecosystems, species coexist, compete, and cooperate to shape each other's evolutionary pathways. This interconnection emphasizes the importance of relationships and interactions in the development of complexity, both in space and in living systems. The parallels drawn between cosmic and biological evolution highlight common themes of gradual change through incremental processes, the role of randomness, self-organization, and the interconnectedness of components. By exploring these similarities, we can gain a deeper understanding of the underlying principles that govern both the universe and life, which will facilitate an interdisciplinary dialogue between cosmology and biology. Linguistic structures play an important role in shaping our ability to discuss and theorize about complex concepts such as nothingness and the early universe. How we formulate language not only reflects our thoughts, but also influences how we formulate ideas and communicate abstract concepts. This relationship between language and thought can have a profound impact on our understanding of fundamental cosmological ideas. One of the most important aspects is how the language we use can limit or facilitate our conceptualization of nothingness. In many languages, the term nothing is loaded with meanings that may limit our ability to fully understand the idea of total absence. For example, the use of negative constructions in sentences often relies on binary oppositions such as something and nothing, which can inadvertently anchor our thinking to a more dualistic understanding of existence. As a result, discussing nothingness becomes challenging because our cognitive frameworks are often not designed to readily accept the absence of concepts. This limitation can affect philosophical and scientific discussions about the nature of the early universe, where ideas about the vacuum or conditions before the Big Bang are framed within existing linguistic structures. In addition, the vocabulary available for discussing abstract concepts greatly affects the complexity of the ideas that can be communicated. For example, rich terminology in physics and cosmology allows scientists to expound subtle theories about the origin of the universe, while the absence of such terminology can impede progress. Developing a precise language to describe phenomena such as quantum fluctuations or singularities may increase our collective ability to grasp these ideas, stimulating further study of the early universe. Theoretical insights may be related to how effectively such concepts are communicated through language. In addition, linguistic structures can shape cultural views on concepts such as nothingness. Different languages and cultures may have unique approaches to discussing the void or conditions that existed before the creation of the world. These culturally fixed linguistic frameworks can influence societal perceptions of cosmological principles and even dictate the philosophical implications associated with non-existence. Such cultural perspectives play a role in guiding scientific research and encouraging some interpretations over others. Moreover, cognitive linguistics argues that the way we construct sentences can influence our thought processes. For example, languages that use metaphors, analogies, or spatial representations can influence how people formulate their understanding of abstract ideas. If a language encourages a narrative or framework that allows for flexibility in how the universe originated, it may lead to more innovative theorizing. Conversely, rigid linguistic structures can inhibit new approaches to discussing fundamental cosmic concepts. Linguistic structures significantly influence our ability to discuss and theorize about nothingness and the early universe. The limitations and richness of our language can shape conceptualization, guide scientific discourse, and reflect cultural perspectives. By recognizing the relationship between language and thought, we can strive to develop better ways of formulating abstract ideas, which will ultimately improve our understanding of the fundamental nature of being and the cosmos. Complexity theory provides valuable insights into the origin of the universe by exploring how simple components can interact to give rise to complex and emergent systems. This view emphasizes that the universe is not simply a collection of isolated elements, but rather a dynamic network. Complex structures emerge over time as a result of interrelationships and interactions. One of the key points of complexity theory is the concept of emergence, which describes how new properties or patterns emerge from the interaction of simpler elements. In the early universe, fundamental particles such as quarks and electrons interacted according to the laws of physics, leading to the formation of atoms and later stars and galaxies. By viewing the universe through the lens of emergentism, we can better appreciate how simple initial conditions shaped by physical laws evolved into the rich tapestry of structure we observe today. This view challenges reductionist approaches that seek to explain the universe solely by examining its individual components. In addition, complexity theory emphasizes the importance of feedback loops and nonlinear dynamics in the evolution of systems. The expansion of the universe after the Big Bang and the interactions between cosmic structures can be viewed as complex systems that exhibit nonlinear behavior, where small changes in initial conditions can lead to very different outcomes. This concept parallels the ideas of chaotic systems, where predictability can be lost over time. Understanding these dynamics allows researchers to build more accurate models of cosmic evolution, covering everything from the formation of galaxies to the distribution of dark matter. In addition, complexity theory encourages interdisciplinary approaches to the study of the origin of the universe by incorporating aspects of sociology, biology, and computer science. This broad perspective can foster innovative methodologies to provide new insights into how complex cosmic phenomena operate. For example, models originally developed in fields such as ecology or network theory, where the principles of interconnected systems are similarly applicable, can be used to study the formation of large-scale structures in the universe. Another intriguing aspect of complexity theory is its emphasis on the adaptability and resilience of systems. The universe has gone through various stages of evolution, from the formation of the first atoms after the Big Bang to the emergence of stars and galaxies. Adaptability is manifested in the way structures persist and evolve despite changing conditions and cosmic events. Recognizing these features in cosmic evolution may improve our understanding of how resilience arises in biological systems, leading to a more complex view of nature. Complexity theory offers a deep understanding of the origin of the universe, emphasizing the role of emergence, nonlinear dynamics, interconnections, and adaptability. By applying these principles, scientists can further understand how the universe evolved from simple initial conditions to the complex and intricate cosmos we observe today, fostering interdisciplinary approaches that expand our understanding of both cosmic and biological phenomena. Computer science concepts, particularly information theory, have intriguing applications in the field of pre-Big Bang physics, providing a framework for exploring the nature of information, entropy, and the underlying order of the cosmos. These principles can enrich our understanding of the early universe and the conditions that may have existed before the Big Bang. One of the central applications of information theory in this context is the concept of entropy. In information theory, entropy measures the amount of uncertainty or information contained in a system. Similarly, in cosmology, entropy is a critical factor in understanding the state of the early universe. Before the Big Bang, the universe is believed to have been in a state of high homogeneity or low entropy, where matter and energy were uniformly distributed. Understanding how information and entropy are related can help physicists study how small fluctuations in this homogeneous state could have produced the structures we observe today, including galaxies and cosmic filaments. In addition, information theory emphasizes the importance of data transmission and storage, which can serve as an analogy for understanding processes in the early universe. Just as information can be encoded and transmitted in different systems, so fundamental physical processes in the pre-Big Bang era may have involved encoding energy and matter in ways that laid the foundation for the evolution of the universe. Exploring these ideas within the framework of information theory allows researchers to think critically about how energy and information were interconnected at this primordial stage, leading to discussions about the fundamental nature of reality itself. In addition, concepts such as the holographic principle, which suggests that all the information of the universe can be encoded on a lower dimensional boundary, may overlap with ideas from computer science. This principle implies a profound relationship between information and the physical structure of the universe. If the information content of the universe is fundamentally related to its geometry, then computer science's knowledge of data compression and encoding can be valuable tools for understanding how complexity emerges from simpler components in a cosmological context. In addition, in recent studies of quantum mechanics, scientists have identified interesting connections between quantum information theory and cosmology. Studying quantum entanglement, superposition, and particle behavior at a fundamental level can spark ideas about how information is processed in the fabric of the universe. This leads to questions about what role information may have played in the transition from the pre-Big Bang state to a more complex universe. Information theory provides powerful concepts that are applicable to pre-Big Bang physics, illuminating the relationships between entropy, data encoding, and the fundamental nature of the universe. Using insights from computer science, physicists will be able to further explore the complex relationships between energy, matter, and information, ultimately deepening our understanding of conditions that existed before the cosmos as we know it. Sociology offers a valuable perspective on how scientific communities develop and accept theories of the early universe, emphasizing the social dynamics, cultural influences, and collaborative processes that shape scientific knowledge. Understanding these sociological factors can shed light on how theories develop, gain momentum, or face resistance in the scientific community. One of the most important aspects is the role of social networks and collaboration in the development of scientific theories. Scientific discoveries often occur through the collaborative efforts of researchers from different disciplines. In the field of cosmology, the exchange of ideas and data between scientists can foster a more inclusive environment where different perspectives are considered, allowing for a richer discussion around theories of the early universe. Sociologists explore how these networks facilitate communication, allowing researchers to build on each other's work, leading to the refinement and evolution of theories over time. In addition, the process of reaching scientific consensus is shaped by sociological factors. Acceptance of new theories often requires validation and endorsement by respected experts and institutions in the scientific community. The need for peer review can lead to the phenomenon of scientific scrutiny, where some theories gain prominence while others are sidelined based on the social status or authority of their proponents. Sociological research can help reveal how power dynamics and authority influence the prioritization of theories, shedding light on the mechanisms by which scientific communities reach consensus around complex ideas about the early universe. Cultural context also plays an important role in the formation and reception of theories. Scientific progress is not isolated from cultural beliefs and societal values, which can shape research priorities and influence funding decisions. In the case of theories about the early universe, broader public interest in understanding the origin of the cosmos can stimulate funding and media attention, creating the conditions in which specific theories become prominent. Understanding this interaction between culture and science can provide insight into how societal narratives can influence the acceptance of certain cosmological models. In addition, sociology emphasizes the importance of public and educational involvement in the development of scientific theories. The ways in which scientific ideas are communicated to the public can have a profound impact on their acceptance. Engaging the public through accessible accounts of the early universe can foster interest and understanding, which in turn can influence how scientific communities perceive the relevance of certain theories. Positive public attitudes can lead to increased funding and support for these areas of research, influencing which theories are further explored and accepted. Finally, the study of scientific revolutions proposed by sociologist and historian Thomas Kuhn shows how paradigm shifts can lead to the adoption of new theories. When existing concepts are confronted with anomalies they cannot explain, such as new observations related to the early universe, scientific communities may experience crises that prompt a re-evaluation of established ideas. Sociological analysis of historical shifts in thinking can help identify factors contributing to paradigm shifts, providing a context for understanding how today's theories may evolve in response to future discoveries. Sociology makes a significant contribution to understanding how scientific communities develop and accept theories of the early universe. By examining the role of collaboration, consensus building, cultural context, public engagement, and paradigm shifts, we can further understand the social dynamics in scientific inquiry and how they ultimately shape our understanding of the cosmos. Economic models of resource allocation offer intriguing parallels to the distribution of matter and energy in the early universe, emphasizing that both systems can be understood through principles of distribution, scarcity, growth dynamics, and evolution. By studying the similarities between these processes, we can understand how the universe evolved from a homogeneous state to the complex structures observed today. One of the fundamental concepts of economic models is the distribution of finite resources, which is directly related to the distribution of matter and energy in the early universe. Shortly after the Big Bang, the universe was characterized by a nearly uniform distribution of energy and matter. As the universe expanded and cooled, quantum fluctuations created fluctuations that led to localization of the density of matter. Similarly, in economic systems, the distribution of limited resources can lead to inequalities and differences in access. The way these resources are distributed may parallel how gravitational forces in the universe gather matter to form galaxies, stars, and planets, reflecting a denser distribution of resources within a larger structure that is expanding. In addition, concepts such as market dynamics and competition can serve as valuable analogies to cosmic processes. In economics, competition between agents drives innovation and efficiency improvements, which can be compared to the competition between gravitational forces that determine the formation of structures in the universe. For example, areas with higher concentrations of matter can attract more mass, leading to the creation of complex systems such as galaxies. This competitive aspect parallels market forces in economies, where actors seek to optimize their positions in resource allocation, leading to unequal but sometimes beneficial outcomes in the context of growth and stability. Another concept common to these fields is the feedback process. Economic models often illustrate how feedbacks between resources, such as reinvestment or depletion of resources, can affect their future availability and distribution. In cosmology, the dynamics of matter and energy also exhibit feedback mechanisms. For example, the accumulation of matter in galaxies can increase gravitational attraction, attracting more matter and promoting further growth. Understanding these feedback loops, whether in an economic context or in cosmic evolution, helps illustrate how small changes can lead to significant, sometimes unpredictable outcomes over time. Moreover, the study of entropy and thermodynamics, which are often used in economic models to analyze resource allocation and scarcity, has parallels with cosmological processes. In economics, the second law of thermodynamics can help explain how systems evolve toward equilibrium. In the early universe, as it expanded, the distribution of energy and matter increased entropy. As structures form as a result of gravitational clustering, the energy states of the universe change, leading to a more organized distribution of matter, just as economies move from a state of scarcity to a state of organization and stability. Economic models of resource allocation are related to the distribution of matter and energy in the early universe through the concepts of distribution, competition, feedback mechanisms, and the evolution of systems over time. By recognizing these parallels, we can deepen our understanding of both economic systems and cosmic evolution by highlighting how complex interactions can give rise to rich structures and dynamics in seemingly disparate domains. Music theory offers a fascinating look at the concepts of harmony and symmetry in the cosmos, revealing deeper connections between art and science. The principles of music, especially those related to harmony, rhythms, and structures, can serve as an analogy for understanding the interrelationships and patterns in the universe, improving our understanding of cosmic phenomena. One key area where music theory intersects with cosmology is the concept of harmony. In music, harmony refers to the combination of different tones or tones that create a pleasing sound or balance. Similarly, the universe exhibits harmonious relationships through the interplay of fundamental forces and particles. For example, the fundamental forces of nature, such as gravity, electromagnetism, and nuclear forces, can be viewed as a symphony of interactions that govern the behavior of matter and energy. Just as harmony in music is achieved through the careful arrangement of notes, the balance between these forces creates the complex structure and behavior of the universe, leading to the formation of galaxies, stars, and even the conditions for life. In addition, symmetry plays an important role in both music and the cosmos. In music, symmetry can be observed through patterns and repetition in melodies and harmonies, creating a sense of balance and coherence. In astronomy and physics, symmetry is a guiding principle that helps describe the laws of nature. For example, conservation laws in physics, such as conservation of momentum and energy, are often based on symmetric properties. In particle physics, the symmetries associated with fundamental particles dictate their interactions and behavior at the quantum level. Understanding how these symmetries manifest in the cosmos can provide insight into the fundamental structure of the universe itself, just as symmetry creates structure and form in musical compositions. Another area in which music theory provides insight is the use of scales and intervals. Musical scales, consisting of specific intervals between notes, set the framework for creating melodies and harmonies. Similarly, the relationships between different physical quantities in the universe, such as time, space, and energy, can be viewed as a kind of scale. For example, the concepts of redshift and blueshift of light from distant galaxies can be compared to musical intervals that convey motion and change. This analogy emphasizes the interplay between frequency and energy in sound and light, enhancing our understanding of phenomena such as gravitational waves and cosmic expansion. Furthermore, the use of rhythm in music can be correlated to the cyclical patterns observed in cosmic phenomena. Celestial bodies, such as planets and stars, exhibit rhythmic behavior in their orbits, often reflecting predictable patterns due to gravitational interaction. This cyclical behavior can be compared to rhythmic patterns in music, where beats and measures create a sense of order and predictability. Recognizing these rhythmic patterns in the universe helps us understand complex systems and the dynamics that govern them. Insights from music theory concerning harmony, symmetry, gamma, and rhythm can deepen our understanding of the cosmos. By drawing parallels between the structured beauty of music and the complex order of the universe, we can appreciate the underlying principles that govern both realms, enriching our perception of existence and the relationships that bind us to the cosmos.